Let's have a look at scalar and vector resolutes, a vitally important area in the understanding of vectors. So let's get into it without any further ado, and we'll explain it. Hopefully you'll really get it, because it's a simple, logical concept, and there's really nothing to it if you understand it. So come on, let's go. Setting the scene. Now, setting the scene, what I'm going to do for you is I'm going to start back at something you do really understand, which is basic trigonometry, and I'm going to draw you a triangle, and from that we're going to lead to scalar resolutes, and from there we're going to get to vector resolutes. So that's the way it's going to be. See that triangle there, U, V, W, capital U, capital V, capital W? If I put side labels in there for the sides, I'm going to label opposite those vertices with lowercase corresponding letters for the sides, like that. So there you've got capital W, and opposite that, the side opposite that vertex is little side W, okay, which denotes that length there, okay. So now what I've done here is I've just amplified that a little bit. I've showed you that this is really side V, and that there from W to V is side U. I've put an altitude in as well, and I've put an angle theta, which is the angle which is between side V and side U. Okay, next step. Now if we take that triangle there above, by trigonometry, Wx can be determined in terms of the hypotenuse, which is V there, and also in terms of theta, yes? Where did I get that right? Yes, so therefore we can say that cos theta equals Wx over WU, doesn't it? It does, by basic trigonometry from year 10, or even year 9, I think. So you know that, right? So the next step is we can transpose that. We can say it's Wx over V, and we can transpose that to get Wx is equal to V cos theta, all right? Now, okay, no problem. Now we're going to basically use the same diagram, but I'm going to convert it into vectors, so you watch this. So I'll draw the diagram out again, but we're going to use vectors this time to actually arrive at the same formula for Wx, okay? Here it comes. There's my triangle. That's the triangle we've got above, okay? Nothing different there. Everything's the same at this point. But now, when I basically... Now I'm going to transform it. You watch. Okay? So that V and U are going to become vectors, okay? There it is, right? You got it? Now, can you see these gadgets here? That arrowhead and that arrowhead. So we've got vector V and vector U, okay? And we've got the angle theta between them. Now I'm going to arrive at the same formula as above, and you're going to be amazed. So using the same trigonometry as above, okay? Same trigonometry as above, we can get this particular formula which says the length of vector Wx is equal to the length of the vector V times cos theta. Now, look, there's no smoke and mirrors. That's just the same basic expression, okay, where Wx is the vector running from W to only as far as X. All right, you got that? All right, so are you okay so far? I think everything's good, okay? So now, we'll go over the page and we'll keep going. So that's where we got to from the last screen. So basically we know that WV, vector WV equals U, okay? And we can say that the expression we had before was that Wx, the length of Wx, vector Wx, the length of it is the length of vector V times cos theta, all right? Now, as I said, this is the same statement as given before, which was just Wx equals V cos theta before we did all the vectors. But this time we've got these vectors in the equation instead of just side lengths, all right? Now I'm going to give you a couple of definitions, all right? Now, vector Wx, vector W to x, that is from there over to there, right? And going from left to right is called the vector resolute. The vector resolute of vector V parallel to or in the direction of vector U, okay? Right? And also xu is called the vector resolute of V perpendicular to U, perpendicular to U. So what I am saying is, yes, we're saying that as a vector addition, we're saying that WU, which is vector little v, is actually the sum of two vectors. wx and xu, aren't we? That is what I'm saying. That's putting it in lowercase format, which is what I'm probably more used to. So, yes, we're saying there that this is little v, this is little v, which is parallel, the resolute, which is parallel to vector u, and this is the resolute of v, which is perpendicular to u. So v is made up of two perpendicular vectors, right, called resolutes, one of which is parallel to vector u, one of which is perpendicular to vector u. That's why they're called resolutes. Just to make it completely clear, that one there is the vector resolute of v parallel to u, and that one there is the vector resolute of v, which is perpendicular to u. Okay? Are you right with that? That's all it is, guys. It's just vector addition, okay? Except that they're perpendicular to each other, and one is parallel to u and the other one's perpendicular to u. So, all right. Finally, we can say that the length of wx, the length of vector wx, is called the scalar resolute of v, which is parallel to or in the direction of u. So that line from w to x is just a length. It's a length. It's the length of the vector resolute parallel to u of vector v. But it's just a length, so it's called the scalar resolute of v, parallel to or in the direction of u. Okay, so you get that? And of course we know that the length of wx is, as we've established before up here and on the previous page, is equal to the magnitude of vector v times cos theta. Okay, now how's that? Yes? Now, having established this leap of logic here, with this triangle here, it's all very convenient because it's a little bit, this is sort of like in the x direction, if you like, it's sort of horizontal. But this same formula down here applies for any vector u pointing in any direction at all. So, in fact, v can be resolved as a parallel component to and a perpendicular component to any other vector at all. So how can this be? Well, let us see. There it is. Now, that's the diagram we had on the previous page, blown up a bit so you can see what's going on. Now I'm going to put in a different version of vector u for you, which won't be a horizontal one, and we'll show you that the same situation applies. You can have those vector resolutes, one parallel to it and one perpendicular to it, no matter which way v is pointing. Right, that one's called u1. Now all you've got to do, guys, is to work out what those resolutes are, is basically just draw a line through the point there where the head of the arrow of vector v is, but perpendicular to that green line, and then you've actually the point of intersection down here somewhere. Point of intersection down there somewhere is going to be the point where the parallel resolute joins the perpendicular resolute. Yeah, so I'll show you anyway, in case I'm rabbiting on here. There it goes. You see those yellow ones? So what I've done is I've called that thing vector. No, not vector. I mean angle θ1, and this vector up here is the resolute of v, which is parallel to u1, and this one going up this way is the resolute, the perpendicular resolute. The resolute of v, which is perpendicular to vector u1. Are you getting me? See? You can do it. It doesn't matter which way u's pointing, you can still do it. I'll do another one for you now. That red one, that's u2. Now, come and you imagine now, which way would the parallel resolute go and which way would the perpendicular resolute go to get from w up to u? Well, here it comes. There it is. There it is. Okay? So this one here is the parallel one. This one here is the perpendicular one to vector u2. Okay, so that's how it goes, and then you can just keep on going with any old one. In fact, I'll show you another one over the page, which is a bit more challenging, because in this situation over the page we're going to do something where the angle between v and some other vector u will be an obtuse one, not an acute one. So that's harder to visualize what you do. So let's have a look at that. Here comes our triangle. And yeah, that's the triangle we had before. Now, so let's check that out. There's vector u3 there. A bit strange, you might say. Yes, because this angle here is obtuse, very obtuse. So how do you do? How do you do two vectors which make up V, starting from W, ending up at U, one of which is parallel to this beast and one of which is perpendicular to it? Well, ladies and gentlemen, actually, it doesn't look easy, does it? But it is, because you watch this. It's the same procedure applying for the scalar and vector resolutes, because the parallel component, which is parallel to U3, also includes minus U3, or going in the opposite direction to U3. So if we do that, look at that. See? Easy as 1, 2, 3. Parallel and perpendicular to U3. Yeah, see? That's how it works. It's easy, isn't it? See, now you can see I went from W, I went parallel right along U3 actually, and then I went perpendicular to it and I got up to U. So that's how you do these things, right? So now I'm setting you up for, we're going to, now in the next screen we're going to derive the formula completely in terms of dot product for the scalar resolute and then the vector resolutes of these, of the V's onto U and perpendicular to U. Alright, now, okay, so what are we saying? We're saying, let's just recap. We're saying that the length of vector Wx is called the scalar resolute. Just the length, that is called the scalar resolute of V parallel to or in the direction of U. Okay, and we know that the length of Wx is equal to V, length of V cos theta, don't we? I think we do, because we established that already. That's nothing new. I'm just not telling you anything new there. That's all old stuff. There's our triangle. Now, here we go. I'm going to progress this a bit further now. The length of Wx, which is the scalar resolute of V onto U, can be re-expressed in terms of a dot product. Completely re-expressed in terms of a dot product. So let's just go with that. I'm saying to you, what am I saying? I'm saying that Wx, the length of Wx is equal to length of V cos theta. Now, here we go, starting with that. That's what we know. That came from the basic trigonometry, remember? Yes, basic trigonometry. Now we're going to multiply top and bottom by magnitude of U over magnitude of U, which is in effect just 1, but I'm going to pull out of a rabbit out of a hat in a minute, so watch this. So, right, that's where we get to. Now, can you see this up here? What does that look like to you? Look, magnitude of U times magnitude of V times cos theta, good grief. If that was, that's a scalar dot product, if ever I saw one, isn't it? So I can re-express that as V dot U over magnitude of U. But it's not finished yet. It is in terms of dot product, but you can even clean it up a bit nicer, more nicely I mean. So, excuse me, having a little cough. U over magnitude of U, vector U over magnitude of U is called, what is it called? It's called U hat, which is a unit long vector in the direction of U. Now we covered that in a previous presentation, so I can rewrite that expression there with the U hat in there. So it's V dot U hat. That's it. That is, now I know it looks weird, I know, but it's, look, it's the length of Wx. It's the length of Wx, which is a scalar resolute of the vector V onto the vector, or parallel to the vector U. Okay? So there you have it. There's the first definition I need you to know and understand and learn. The scalar resolute of vector V onto or parallel to vector U is equal to V dot U hat. Now, if you forget which one gets the hat, it's the one where you just go back to basic trigonometry. Draw the triangle. You want V cos theta, don't you? Well, if you've got something like this expression here, that expression includes in it V dot U includes the length of U. And you don't want the length of U. It's got nothing to do with anything. We just want the scalar resolute of V onto that horizontal side of the triangle, WV. Yes? So that's why you want the U hat in there, because that means you're dividing by the length of U. I cover that more over the screen. So that's where we got to. The scalar resolute of vector V onto or parallel to vector U is V dot U hat. And I've just written here in red, basically just to remind you that if you, I want you to remember basically that the vector we are resolving onto, in this case vector U, is the one that gets the hat, all right? It's the one that gets the hat. And I've written there in a big, nice, thick red line to emphasise what I'm talking about here. This line, Wx, is the scalar resolute of vector v onto vector u, right? So let's just repeat it again. Length Wx equals v dot u hat, which is a scalar resolute of v onto u, all right? Now, lock that in. Now we're going to take it another step now, and we're going to get to the formula for the vector resolute. That would be vector Wx, all right? Okay? So, to take this to the next step, vector Wx is the vector resolute of v onto u. It is, right? It's a vector, right? How do you express that? Well, it's very, very simple. Vector Wx has length of that, right, which is the length, that's the length, which is actually the scalar resolute, as we found above. The length of that line Wx times u hat, which happens to be a 1 unit long vector pointing in the direction of u, as I've given you this information here, as I've told you here. Right? Does that make sense? Vector Wx equals the length of the line Wx multiplied by a 1 unit long vector pointing in the direction of u. You get that? Yeah, so here it comes. That's what that is. That is a vector pointing in the direction of u with length of Wx in parallel lines. So you express as a length. Yeah, do you get that? Okay, so now let's just get your formula happening here for in a neat vectorish kind of way. Okay. So therefore we're saying that the length Wx equals a scalar resolute of v onto u. So we're able to substitute that formula that we found up here. That's this one up here, right? We're going to put that in there, in there, right? So that's going to get us our formula for the vector resolute. So here it comes. Yes, that's right. And here we've got, yes, therefore Wx, the vector resolute of v onto u, is equal to the length of the scalar resolute times vector u hat. Yes, oh my hat, you're saying, don't worry. You'll get used to it. It's very, very logical. Very logical and very simple once you grasp it properly. So the vector resolute of v onto or parallel to u is, yes, there it goes, it's v dot u hat, which is a scalar resolute, times u hat, and that now turns it into a vector. That's it, right? That is our formula. So now there is another easier version which I'm going to cover over the screen for that formula for the vector resolute parallel to u. And this is the way I do it. I'm just going to derive it for you. So we know that the vector resolute of v onto u is what we just got over the page, which looks totally Weirdsville, I know, but it's not that difficult, as I say, because the first two symbols just get you the scalar resolute, or the length of the line, times the vector u hat gets you the actual vector. Now, let's just massage that a bit. What am I doing there? Yes, I'm putting it into the form that you the way I like to think of it. I put brackets in there to just distinguish the part which is the scalar resolute. Yeah, because otherwise you can get very, very flummoxed and confused with all this. Now what we're going to do is we're going to put that in a different form where we're going to actually get rid of the hats and just put the vector u hat as u over its length. All right, and in the next line, I'm going to put this in there, and I'm going to do an abracadabra for you, and you will see something amazing. Yeah. Now, what have I done there? While all that red writing's writing, what I've done here, guys, I've rewritten magnitude of u times magnitude of u as u dot u, because they're the same thing. U dot u, just remember, u dot u is magnitude of u times magnitude of u times cos of the angle between them. If they're the same vector, cos of the angle between them is cos of 0, which is 1. So you just get magnitude of u times magnitude of u. So this can be re-expressed in this simple format. The vector resolute of v onto u is v dot u over u dot u times u. And that's really, really nice. I really like it. And there's the summary of it. So the two different forms, whichever one you like better, you can use. Okay, there's the first one we got, there's the second one we got there. Okay, now the reason that I like this better is explained here. I find it easier to work with because basically the first version, which is this one here, requires you to work out u hat, and if you want to work out u hat, that means u over its length, and you've got to work out its length, which is a Pythagorean square root thing, all of which is very annoying, and I can't be bothered, because in this version here you don't even worry about it. You just work out u dot u. There's no hats, no nothing, and it's really easy to do, and I just think it's so much more elegant and so much easier to work with. Okay, so I like that version, and I recommend it to you, but you just use whichever one you like. Now, we better summarise where we've got to, because we've covered quite a bit of ground. Okay, so the scalar resolute of v onto u is v dot u hat, we got that, and the vector resolute of v onto u is one of those two things, v dot u hat times u hat, or v dot u over u dot u times u. Okay, remembering that all that bit there in the brackets is just basically a number, right? It's just a number, two dot products, one over the other. That's the vector bit, right? Yeah. Okay, now we're going to do a finally now. We've got to do the last bit. We've done the scalar resolute of v onto u. We've done the vector resolute of v onto u. Now we've got to do the vector resolute of v perpendicular to u. Okay, so there's what we got to there. The scalar resolute, that red line, is the scalar resolute of v onto u. Now, if I cross that out and put an arrow there and make it a purple line, which is a vector, you now have the vector resolute of v onto u, that is vector wx, right? Now we're setting the scene for the last little bit of the formulas we have to know. So we're saying that v equals, what does it equal? It equals the vector resolute of v, which is parallel to u, added to the vector resolute of v, which is perpendicular to u, right? That bit there is wx, that bit there is xu. Okay, better write xu, yeah, there it is, and yeah, that's that one there. Okay, how you going? Now, therefore, if I want to get the perpendicular bit, that bit there, I just rearrange that formula, that's all I do. And, yeah, I've just actually drawn that thing in there for you, okay, xu, to make it clear. So, therefore, that bit there, the resolute of v perpendicular to u is equal to v minus the parallel resolute, yeah, the resolute of v which is parallel to u. Okay, put a box around it and Bob's your uncle. So, and I'm just emphasising down there, you calculate v parallel to u, you subtract it from v to find v perpendicular to u. So, okay, here comes the super duper mega summary. Whoa! So we've got the scalar resolute of v parallel to u is v dot u hat. We've got the vector resolute of v parallel to u is v dot u hat in brackets times u hat, or it's v dot u over u dot u times u. And thirdly, we've got the vector resolute of v perpendicular to u is v itself minus the v parallel to u resolute. All right? Righty-ho. We better do an example before we all collapse, okay? Right, I've got A equals 2i minus 3j minus root 3k. I've got B equals minus I plus 2j minus 3k. I just picked those numbers out of the air, so it actually worked out a bit complicated, but look, the principle's good, so I want you to follow along with me. What are we going to find? We're going to find A, the scalar resolute of A onto B. We've got to find the vector resolute of A onto B, and we've got to find the vector resolute of A perpendicular to B. All the things we've been covering. So let's do A today, and first of all we're going to get the scalar dot product, A dot B. Now that's easy, I showed you how to do that in a previous presentation. There it is, and what does that come to? It comes to that, which comes to that. It's, what is it? 3 root 3 minus 8. So therefore we can work out the scalar resolute of A onto B, which can't have any length component of B in it. So it's going to be A dot B hat. So we've got to divide that result by the magnitude of B to get A dot B hat. Okay? So there it is. So, and I've actually worked it out. A dot B hat will be that result divided by the magnitude of B, which happens to be Pythagorean thing, square root of 3 squared plus 2 squared plus 1, which I think is 14. Okay, so that little expression there is the scalar resolute of A onto B. For you and me, yippee. Okay, good. Now we'll do B. And what's B again? The vector resolute of A onto B. Alright, the vector resolute of A onto B. Now I'm going to use this is my preferred Wolfe formula here. This is the one I'm going to use because I like this one. So is that alright with you? Hope so. So therefore here it comes. It's okay, A dot B over B dot B times vector B. So look how easy it is. See, there's the A dot B result from the previous line on the numerator, divided by B dot B. Now see, there's no hats anywhere. Lovely, isn't it, right? 1 plus 4 plus 9, which is just that coefficient squared plus that coefficient squared plus that coefficient squared. No hats inside anywhere. It's lovely. And that's vector B, okay, for you and me. So where does that get us? It gets us a very, very complicated expression, Gurk. But nevertheless, it's correct, all right? Now, that's part B. Yeah, Mr. Box, thank you. Now, part C, what are we got to do with this? The vector resolute of A perpendicular to B. Okay, well, that's easy. That's what did I tell you to do up here? Okay, you work out that's just V minus V parallel to U. So, okay, so it's, what's it going to be? There it is. So it's A, perpendicular to B is equal to A minus A parallel to B, which is going to be, yeah, that's easy. There it is. There's A, and there's A parallel to B, which is this one up here. Now, I haven't gone any further because it's a bit of a disaster. You'd actually have to simplify that out a bit and get all the coefficients all sitting nicely with the one I term and so on with the J and so on with the K. But look, it's too hard, and you get the idea. And, you know, it's really easy. It's really easy to do. You've just got to know those formulas and understand them. If you do that, you're going to be absolutely sitting pretty. So, okay, another example, and then we're done. This one here is a very interesting example, and it's a very typical exam kind of question, right? Exam strength. So we've got A is, what is A? A is minus 7 root 3 over 3I plus J minus 2K, and B is I plus whatever it is, root 3J plus 2 root 3K. We've got to find firstly a unit vector in the direction of B. Okay, well that's easy. And I'm going to do this with technology for you, okay, just so that you'll get the hang of how to use the calculator. So a unit vector, come on, what is that? That's B hat, isn't it? Yeah, it's B hat. So we can use the calculator for that, and I've just showed you how to do it. There's a thing in your calculator menu called unit V. It's in the vector menu, and it's easy. What you do is you just plug that in, and then you actually generate a 1 row by 3 column matrix. Not that I'm implying vectors and matrices, but you just use the, you use the matrix kind of things to express vectors on the calculator. So you put that in there, and then you get the answer. That's what you do. There it is. And I've just given you a couple of comments here to help you. Your unit vector is found in the vector menu. Use a 1 by 3 matrix for the inside those brackets there, inside those brackets. Then tab across to each entry and enter the IJK coefficients, and then hit enter and Bob's your uncle, and you get that. So therefore, my answer is B hat is 1/4 of I plus root 3J plus 2 root 3K. Now, you're going to have to make up your mind which is faster, by hand or using the technology, and it'll probably depend on how fried your brain is in the exam by the time you get to a question like this, actually. If you've got 2 hours of full-on maths in a 2-hour exam, your brain's pretty well fried by the time you get to the end of it, so, you be the judge. This one here. We've got to resolve A into 2 vector components, one that is parallel to B, one is perpendicular to B. Well, that's what we've just been doing, guys, isn't it? Yes, I'll rewrite them out. There's A and there's B. Now we've got to do A parallel to B and A perpendicular to B, don't we? Yeah? Well, there's the formula for A parallel to B, and then there's the formula for A perpendicular to B. There's parallel to B, there's perpendicular to B, all right? Now I'm going to use the technology again. Here comes the screen. Wacko, the diddlo, look at this. So I've actually used the dot product function here. There's a dot product function. So that's basically, looks complicated, but that's basically the dot product of A, there's a comma there, and they use braces, curly braces, and commas between these entries. That's the syntax they use. So that's A dot B, and this is B dot B, which I've worked out first. It looks like it's minus root 3 over 3, or minus 1 over root 3 is the same thing. And then what I've done there in the next row is I've multiplied that thing there by B, vector B. That thing there in that square matrixy thing, which is really a vector thing, is just B. So that's A dot B over B dot B times B. And there's your answer. That is the resolute of A parallel to B. Oh goody, fills us with glee, doesn't it? So yeah, we can say, oh yeah, that's what I'm just explaining there. I'm just explaining all that for you. That's what that is. And there's the answer. Okay, I've given you the answer there. That's what it is. That's A parallel to B. Now you could work that out yourself using your brain, but you know, it depends on how mushed up your brain is by the time you get to these questions. And usually they don't make them easy either. They put some awkward fractions and things in them, so you can get pretty messed up if you're not careful. Okay, and the last bit is A perpendicular to B was just simply what I did there was I just said A minus the previous answer, which was A parallel to B, and I got that, and then I just put it into IJK format for you. Okay, there it is. So that's the answer. That's a very typical exam question. All right, happy? All right. So we've got 2 more bits to go, then we're finished. Find the angle in degrees that C makes with A. C makes with A. Correct to 1 decimal place. Now, C. Oh, find the value of M. Oh, goodness heavens. M. Okay, so they're giving us a pronumeral there. Find the value of M such... Oh, I'm sorry, I've got it. Find the value of M such that C equals this thing. C equals that thing. Yeah, okay, and they've given you the angle, 2 pi on 3. Okay, and C's, for some reason they're telling us this, which I'm not quite sure what that means at this stage, but we'll just keep an eye on that. Right, so let's go for this, okay? It's just a matter of solving for a pronumeral, I think, once we're given the angle. We're going to dot C with B, then we're going to set it equal to an angle of 2 pi on 3, and M should just drop out the other end, I would think. So let's just go with it, putting one foot in front of the other. So B is that, and C is that. We better... okay, so let's get the magnitude of B first, because we're going to do dot product here and work out an angle. Right, there's the magnitude of B, which looks like it comes to 4. Here comes the magnitude of C in terms of M, and that comes to that, right? Now that's the first bit. So now let's dot them together now in terms of the IJK dotting sort of process, and we get that. Let's simplify that down a bit. We get to that. Now, let's equate them both together. In other words, what am I saying? I am saying this. I am saying... Oh, yeah, well, I know what I'm saying. Yes, I've got it now. So B dot C is also equal to the magnitude of B times the magnitude of C times cos of 2 pi on 3, isn't it? Right? And cos of 2 pi on 3 happens to be minus a half. And you have to know that, otherwise you're in very deep trouble. So, now we've worked out the magnitude of B and the magnitude of C above. So, and we've worked out that, yeah, and we've got everything. We've worked out that B dot C is this thing. So now we can equate this to that, and I think the rest will be history. Yeah. Okay, so that's what I'm saying is that that's what we worked out up there for B dot C. This is magnitude of B times magnitude of C times cos of the angle between them. Now we're going to solve this for M, which I think we need the trusty calculator to do that. My goodness. Yeah, we'll just plug that into the calculator and solve it, I think. Solve it for M. Here comes the calculator screen. There it is. So, okay, so I've solved that in the calculator. First of all, I just wrote that line out over there. That's what I do with the calculator, because otherwise you do too much in one line, it all goes haywire. So I just say that equals that, and then it just restates it. Then I just go solve, then I just drag that line down into there, and then put comma M, which means solve that thing for M, and this pops out the other end. So that's interesting. I've got 2 solutions. Goodness, did they say the value? They said the value of M. Well, we've got this little card up our sleeve too. I think that might have something to do with it. Let's just, with how to work out which solution doesn't work, I mean. Yeah, alright, so we can say that m equals minus 7 root 3 over 3 according to the calculator, or root 3 over 3. Now, but if m equals minus 7 root 3 over 3, then it appears that C will be the same as A. And of course we know that C can't be the same as A from the question that we got. Right, so therefore that only leaves us with one option for M, which is that one. Okay? Pretty neat, guys. Okay, let's quickly go to the next bit because we're dragging on with time. Part D for you and me. Find the angle in degrees that C makes with A. Well, that's an easy question. That's dot product again, correct to 1 decimal place. Alright, let's go for it. We'll restate our vectors. There they are. Now, let's do the magnitude of A, which is that, which comes to that. Let's do the magnitude of C. That's that, which comes to that. Now, let's dot them with the IJK way. You get that. Just check it, make sure you agree. Yeah, you do. Yeah, you agree. Yes, no mistakes. Good, good. Now, this expression here, we're going to make that equal to the magnitude of A times the magnitude of C times cos of the angle between them, and hence we can solve it for then solve it for the angle. So here it comes. Yeah, okay, forgot that bit. That's A dot C. It comes up to 8 over 3. Yeah. So here we come with the equating. So A dot C is also equal to magnitude of A times magnitude of C times cos of theta, and therefore, now I'm going to equate this bit here is A dot C, and then there's the magnitude of A, there's the magnitude of C times cos theta, and that's the only unknown which we can then solve for. So we can say 8 over 3 is equal to 8 over root 3 times 4 over root 3 times cos theta. I think some cancelling is going to happen here. Goodbye, Mr. 8s, and so I think, oh yeah, look, 3 on the left-hand side and root 3 times root 3 on the right-hand side, they're going to cancel out too. Looks like I've got cos theta equals 1/4. Good gracious me. So therefore we can then solve it for the calculator. The angle whose cos is 1/4 is going to be 75. Now you always got to look at the thingo before you leave the question. They're saying they want it to 1 decimal place, so it's 75.5 degrees, and everybody's happy as, and I am too, because I hope this will really help you to understand these resolutes. You've got to go back and study it, and you've got to understand those formulas. You have to understand them. Don't just look them up on a formula sheet. Know them, understand them, know how to derive them, and know how to get them out of your head from your basic level of understanding. That's the best way to go. And do some practice, and you'll just be great. All right, well, thanks again. Hope you had a good time, and we'll catch you next time. Bye.